Okay. For starters, let's just finish up the discussion from last time. Uh, Hopefully you saw on Slack, I posted the updated code that had the fix in it. The fix ended up being the reason CAR was working for everybody. The underlying problem was class to environment. The CADDR of class was giving you the environment, remember, is a list of two lists. Without putting CAR here, you were getting a list of lists of two lists. So you had your list of two lists contained in another list. That's why you needed the CAR here. I'm not sure why we missed that the first time around, but let's just blame Clancy and move on. So, but that's where the issue was. The issue was our extractor for the environment from the class. So with that in place, with the code we wrote last time, we can now ask, person 2 to give us their age, for example, and it'll give us their age from that. Okay, so right now the way we define a class, so we're defining person to be a lambda that has a list of fields and a list of values, and it's going to be a class based on an empty object with list of fields, list of names. So, this guy is a object version of this. Now, so what we have right now is we kind of have, well, I guess we don't even have the interpreter piece yet. What we actually have is the set of structures for supporting a class inside of our interpreter. But the reality is that a class is actually a type. It's a data type in our language. So while we can go and build a class this way, I mean, remember the sandwich that we've done all semester long is this idea of designing a language, whatever, is decide on the data types. So our first language was just numbers. This language now supports, well, we've decided we can have an object type data type. Let's go to something like Java. Java has both, right? When you were first learning about programming, we talked about the primitive types. These are types built into the language, like int and char and boolean and those guys, those things that are core to the language itself. So our previous language had a core element of just int types. Okay, we could certainly expand it and go farther than that. Not the end of the world. Those types just need to be dealt with differently. For instance, you can't do math with a string type. For example, you would have to treat the plus operator as like concatenation, for example, is how Java handles it. All right, so when we design a language, we have our types, and a language like Java has all of our primitive types that came from C. And then it also has object types. It has some object types that have been built into the language as, let's call it, conveniences. So these are objects that already do things that might be helpful. Whereas it also has the facility for allowing us to create our own objects. All right, that's kind of the key feature of an object-oriented language, is that we can create our own objects in that. It doesn't necessarily specify that we can make our, that there will be that many objects built into it, or even any objects built into it. So what is the simplest language? At what point is in a programming language versus, and really the connection I want to make here is the difference between a, let me do one more slide before this. Just make a connection. And this will kind of actually be a little precursor because I think most of you are also taking 450 next semester, which is the systems programming class. If you haven't already signed up for it, make sure you do that. I'll be sending some stuff out over break for you to look at. That'll kind of, I think, help with the class. But in any case, when we talk about operating systems, usually, you'll ask somebody, hey, what's your favorite operating system, or what operating systems are you familiar with, and what do they say? They say things like, oh, well, Windows, Windows 10, or they say Mac OS. What's the current one? Big Sur or something like that. Is that the current one? Big Sur? I think that's the name of the current one. Yeah, Big Sur. That kind of stuff. Are either of these operating systems? Or they might say something like Debian Linux. Are any of these operating systems? Or what would you call them?
I mean, aren't they specific types of operating systems?
What's the actual operating system for Windows 10? I would call Windows 10, well, not just me. Windows 10 is something called a distribution. So all these guys are distributions. Windows 10, the actual operating system, is something called the NT kernel. It's the new technology kernel. Mac OS, the actual operating system, is a Unix kernel. Debian Linux, the actual operating system, is the Linux kernel. So all these guys are distributions of operating systems. Now, what does that mean? Well, the actual operating system for Windows 10 is something called the NT kernel. These are the bare bones minimum that an operating system needs to have. And what's an operating system? It sits between the end user and the hardware, right? So the NT kernel is the must-have for an operating system to work. Windows 10 has the must-have plus a whole bunch of like-to-haves. So for instance, Windows 10 comes with Notepad. Windows 10 comes with a web browser, comes with other tools, Paint and things like that, that allow you to immediately be productive with that particular distribution, because it's decided that these are the core tools that make the operating system a viable productivity tool, as opposed to just something that technically meets the requirements of an operating system, but really is going to require some user applications to make it a viable tool for people to actually use. Now, a computer programmer could sit down with a Linux kernel and say, oh, I'm going to write all my own software. I'll write my own text editor. I'm going to write my own this, that, and the next thing. And, with enough time and effort, they could probably do it. But the idea is that from a productivity perspective, we pretty much rely on a lot of these things to already exist when we think about the idea of an operating system. That's why these things are kind of used synonymously, right? When somebody says, what's your favorite operating system? And they say Windows 10, you don't immediately slap them and say, well, that's not an operating system, that's a distribution. At this point, we're kind of, getting into the weeds about this. But under the hood, the connection I want to make here is that it's the NT kernel or the Unix kernel or the Linux kernel. These are the actual operating systems portions of this. So what's the simplest language? What's the core of a programming language? So this goes back to my idea of it's going to have facilities for memory, remembering, asking questions, repetition. It'll have facility for all those things. Now, when we talk about remembering, we're really saying what kinds of things do we know how to remember? In our first language, the kinds of things we knew how to remember were integers, right? Just numbers. Well, when we think about language like Java, we know how to remember, bytes and shorts and ints and longs and doubles and floats and booleans. Strings are pretty much a common primitive in most programming languages today. Then we also have object types that are built into the language that might be helpful for us. So we have object types for all of our primitive types, because the Java, if we think of Java as a distribution-based programming language, where we're really saying the core language is what's inside of java.core. That's the basic Java language. It used to be called java.lang. Okay. And then around that, for instance, we have things inside of java.util. Java.util has a bunch of stuff in it that might be kind of convenient tools. It's kind of like running into Home Depot and getting one of those box sets of tools that would be helpful for a certain kind of project, something like that, as opposed to kind of that core set of tools that you can't really call it a set of tools unless you have, these 10 things, something like that. All right, so the simplest programming language is going to have facilities for each of these things, but then within each of these, we get a lot of breakdown. And what's kind of interesting here is out of these three, at first glance, at least what I do is I almost rank these as a hierarchy, like, oh, most important to least important. If you think about it for a second, this breaks down, but just at first you kind of think, oh, well, repetition is more complex than asking questions, which is more complex than remembering. So you kind of think about this as, oh, this must be the hard part. This must be, easier than that. And this must just be trivial stuff. When the reality is, and we saw this from with our first language, is the limitation of our language is mostly driven by this. That variable environment and the kinds of values we can store inside of our variable environment is the core to the types of problems we can solve with a programming language. We saw how relatively easy it was to add things like asking questions and repetition to our language once we had this component well in hand. So remembering is really the thing that drives the flexibility of the language, the kinds of data types that we have. That makes some sense? So when we think about Java, Java is to a programming language kind of like Windows 10 is to an operating system. It has core operating system functionality, just like Java has core programming language functionality, that's then surrounded by a bunch of extra tools that give you kind of quality of life type things. Okay, does that make some sense? So when we design a language, we're talking about, we're going to decide on the data types that are in the language. Then we're going to ensure we have the core constructs that all languages must have. So that is memory, asking questions, repetition, some form of each of those, okay? With really the emphasis being on our variable environment. Even if we look at our object-oriented, I'm going to say language, but it's really it's not quite a language yet, but even if we look at that, notice that we needed to have a memory, a variable environment right from the get-go. Object-oriented languages didn't make sense without a variable environment. And if you think back to much earlier in the semester, one of the very first things we did when we first got into writing our own language was to create a variable environment. And that is the core component. So this kind of gets back to, the job of a programming language is to allow human beings to solve problems in the way that we already tend to solve problems. Now, the interesting part of that, though, is that, you almost say it a little bit jokingly, when you first introduce it, but, I think we often take for granted how debilitating it would be if we didn't have our memory. You know, any of us who have family members who have had dementia or something like that, you know, where they just don't recall things as much as they used to, or they don't recall very much at all. You know, it really is a debilitating type thing. And it's kind of the core of all of our programming languages, is that idea of being able to remember stuff throughout the life of a program is the most important piece. So really the flexibility of our language comes into what are our data types. Now look at our language already here. Now we've assumed some data types here because, you know, when we start having objects, it no longer just makes sense for us to just hold numbers, right? You know, we can create a person object, and if we can only hold numbers, then we'd really only be able to hold their like age, their height, maybe height in inches, something like that. You know, but if we're really trying to represent objects, objects have other fields associated with them, other attributes other than just things that can be described as numbers. So in our example right here, we're storing, you know, really, you know, 2 strings and a number. So right off the bat, assuming that we have strings in here, but moreover, we're actually saying we have a new kind of data type, a new kind of animal called a class. So we design a language, we decide on the data type, we ensure we have the core constructs. These are still the planning stages. But the core constructs, we have to have a type for memory management, the ability to ask questions, and repetition. At the very least, our interpreter has to have those things. And then what do? We decide on a syntax, right, and in a parser to convert syntax into, let's just say, logic components, probably objects, but you know, some kind of programmable representation. That's it, logic representation. And then write an interpreter to run the code. All right, so these are the steps to designing our language. If we go back to what we have so far, we've built our memory environment. We've decided on one data type so far. You know, realistically, we have 3 data types being represented here. We have a class, we have an int, and we have a string. So really we have, let's call it 2 primitive type data types, kind of calling strings primitive types in our current world. They kind of bridge the gap between the 2, let's say. But let's say 2 primitive types, and then we have 1 object type, which is the top level object type. And in order for that guy to exist, we had to create the concept of an empty object, that top level object. So this guy had to exist before the concept of an object could even exist. All right, that makes some sense. So then what comes next? So, you know, we wrote our send message stuff to you know, make this all work, and it's pretty much what we wrote last time. I just separated it into a message mapper. So if actually we walk through that real quick, just to see how I use the mapper, it has to do with a list of parameters. If you remember where we left off last class, we weren't even getting it to find the function. So when we go to send message, what does send message do? It calls send message helper. So this is taking the class instance, it's taking the message, and then the parameters you're passing it. So here's me saying send message, here's my instance, here's my message, and here's my parameters as a list. That's what send message is getting. It's then immediately calling send message helper, passing it that class instance and the message. And this guy is boiling down to a lambda. This initial message here, the expectation is that this guy will be found as a function in there. So I am calling this function on these parameters. So what this guy right here does is it says, find me the function that boils down to that is this message from this class instance. That's what send message helper does. Now notice here in send message helper, we get our class instance, we get our message, and we piece these things apart. So let's just take the first part of this initially, then we'll look at what it's doing to the rest of it. So send message helper is going to have our environment, and our environment is going to extract from our class. This is our class instance. The environment, this is where we had the problem initially. Now the extractor works. We're then going to apply our environment, in our environment, the message. So in our case here, we're looking for get value in that environment, and we won't find it at the person level. And we're also grabbing our parent. Then we're asking the question, if answer is not equal to false, which means we found it, then just boil down to our answer. So in this case, answer would be our lambda for get value. But we didn't find it yet because the first place we checked is we checked in the variable environment associated with person. So the first time through here, we did not find it. So we didn't get in here. Then we asked the question, if answer is false and we're not looking at no parent. This is where we got hung up last time. And we thought the problem was comparing no parent, but actually the problem was we weren't even getting down here because of the check here, apply ENV. That's where it was breaking. All right, so we thought our error was in one place. It was actually in another place, and it was because of our extractor. All right, so otherwise, if our answer was false, but we still have a parent, we have another place to check. That's what this says. If I didn't find it here and I have another place to check, then what do? I call send message helper, passing it my parent and the same message. All right, so that bounces back up. We call send message helper again. We extract the environment from the parent. In this case, with just one level up, this is our empty object, which does have our message for get value. Then we get answer, we call apply env on get value in that environment, and we will get the lambda associated with get value there. And if you just want a reminder, this is get value. So get value is a lambda that takes in a variable name, but also takes in a pointer to itself. We were writing Python-based object-orientedness where we have to pass in pointers to ourselves so we can still access things. And then what did we do? We went through and looked up the, well, we got the variable name. We got our answer inside of the parent, ultimately getting the piece of information. So here, when we have a let rec where we have a bunch of name value pairs. So we have one that's a function called check parent that has a lambda, and this guy takes in two parameters. It takes in a class and it takes in a variable name, and we try to get that variable name from that class's environment. We also extract the parent in case we need it again. If I found it, great, return it. So this is like looking for the first name or the last name or the age. Otherwise, if I have another place to check that parent. Otherwise, return false, I didn't find it. This is for getting the value from a particular class. But the punchline for us is, what is the value of get value? It's a lambda. So it's a function. Get value is a function. So back to send message helper. Send message helper then says, so when I finally, well, in this case, I did find it, right? So we pass back through, answer will be equal to that lambda. I'll go ahead and get my parent, which would be no parent, but it doesn't matter because I did find my answer. So if answer is not equal to false, boil down to answer. So what happened right here is send message helper. this guy right here, it boiled down to a lambda. Okay. And then what did I do with that lambda? I passed it my class instance. That's what goes in for self. And I passed it, in this case, just my first parameter. Okay. Because right now we're assuming what we're looking up is going to be a just one thing to make it work for age or just one of our fields. Get value is built into our empty object because it knows how to retrieve the fields from an empty object. Okay, but again, these are the parameters coming into this guy. And what kind of value is Mike or Littman or 21? These are all literals, right? These are literal values that do not need to be resolved. Now, what if I were to pass in a variable here, kind of take this down one more step and say, you know what, I'm actually going to be taking in, what am I passing it? I'm not passing it age. I'm passing it whatever is stored in my variable called LOL, for example. We would then need to resolve LOL to be its value before we can pass that value into get value. Okay, and that's where we might need to map stuff for send message. We might need to effectively map our send message helper across all the elements of our list of parameters until I got everything resolved down. But right now we have nothing to resolve because they're just literals. So that's why I kind of have this here as a placeholder, but I'm not actually using it in my current code. All right. And we're going to see this once we get into writing the interpreter versus writing the parser. And we're not going to get deep into this, obviously, based on time, but I think you're going to see that pretty quickly. This is just going to become another exercise, just like in our previous language, where once we had the core components of it, we could just add feature after feature after feature, and it just worked. So this isn't going to be a major deal as long as we make that jump. All right. So now what we'd like to be able to do. All right. So before I go on, are there any questions about how send message works now that I have that? Most of that code is the same as we wrote last time, with the exception of the bug fix to the extractor. Okay. So one thing we probably don't want to do is we don't want the syntax of our language to be like this. If we're defining a class, so remember, when we think about this, like from a Java perspective, we define the blueprint for a class, and then we create instances of those classes, right? Those are two separate properties. There are two separate activities that are related to each other. All right. So if we are effectively describing this, that's what I'm doing right here, right? I'm saying I want to create a class called person, and my class, all classes have a list of fields, and they're going to have a list of associated values for those. And that's what gets passed into the constructor. And this guy is going to be built in terms of an empty object, passing it those same things. I probably don't want to, and then I also don't have methods. So this is my list of method names, and this is my list of method values. And then we glue these together when we actually build it, right? Empty object does a better job of that because it actually does have things in those last pieces. We don't have fields inside of empty objects, but we do have a single method with a value associated with it. And then when we create a class, we create pairs for scope, which merges these two guys together. We append those two lists together to create our pairs for our scope. So we actually put our methods and our variable and our fields all in the same place, because it's a variable environment for all that stuff. We just happen to pass them in separately because we think about when we write a class in Java, we kind of have our fields at the top, then we write a constructor or two, then we write some methods. So they are in separate places. So this just exaggerates that. But again, these are representations in code for our stuff. When we define in our new language a person, we don't want to write it like this. We want to have a syntax for defining a person. So maybe we want to say something along the lines of syntax for a class. You know, in Java, what do we say? We say class, person, and then we have our opening curly braces, then we list our fields as name value pairs, right? Now, usually, because right now we've taken some liberties with our constructor, and we said that, oh, well, the constructor is automatically created for us. Right now, our class structure, we won't have time to go beyond this, but our class structure basically says the job of the constructors is to just marry field names with their values. That's the entirety of what the constructor can accomplish. If you want to accomplish something beyond that, you have to write it into your own method, which means we then have to have a syntax in our language for describing our own methods, which is why we don't have those yet in what this isn't even a language yet, but in our language in progress. So we have to decide, how am I going to describe a person? Really, how do I write a syntax to describe a class in terms of its fields? So what should my syntax look like for a class that has a name and a collection of fields? That's what we expect in a class, right? So, something like class, person, F name, L name, age, something like that. Those are the pieces of information that we need to express when we are building a blueprint for a class called person. Ultimately, when we create an instance of a person, so right now, this is the blueprint for this guy, but when we create an actual instance of this guy, it's going to be built on top of our base class. So if I go back over to here, you see I defined person here to basically be a list of, it has a name, it has a list of fields, and a list of corresponding values, and it automatically builds itself on top of the base class. All right, so this, I need a syntax for describing that part, because this part is always going to be the same, right? That's our hard-coded logic. This is what our parser is going to produce. Our parser will produce something like this, given a syntax that we describe over here. So we have to decide, what does our actual syntax look like? Now, we've been using a list-based syntax. So maybe it's called, a class called person. And then maybe this guy has his list of field names, something like that. We can say that this is what we want to create. We want to create this. This is our syntax. I want to create a class called person that keeps track of these three pieces of information. And then we want a parser who's going to go through and turn find code to be that guy. Make sure this thing runs. I don't have any errors in that. Okay. So I'm going to have a list containing the word class, maybe lowercase, then the name of the class. So in this case, I put person, and then the attributes we're going to keep track of in that class. All right. And then we want to define our parser to be a lambda that takes in some code, and it will then do some stuff to that code to ultimately produce something that looks like this. So I'll go ahead and start it off here since we only have one type. So we'll go ahead and we'll say I'll do this inside of a let. So we'll say let type be the car of code. So then we'll have a cond equal type class. If that's true, then we need some logic here. I'll just put it as a thing like that so it'll actually finish. And we won't even put an else on this because we only have one type of thing right now. All right, so this is what our parser currently looks like. We need to write the code here such that something that looks like this, I'll go ahead and call it. We say parser, passing it code, such that when I call parser on code, it gives me something that looks kind of like this. This guy up here. It'll create for me, you don't have to worry about the define part. It'll create for you this, a function that ultimately boils down to this, a class based on empty object with your list of field names and your list of field values. This is what it needs to produce. This is the code equivalent. This guy right here is the code equivalent of this. Does that make sense? So your output should be something that looks, what is it? Is it semicolon like that? Should be something that looks like this. So I'm going to save this. I'll go ahead and push it to GitHub. Changed. So now take a couple minutes and attempt to write we're writing just the parser. So all the stuff up above here doesn't even mean anything right now. We're just working with this little world. We're creating a parser that takes in some syntax. And here's the example syntax. And what it should do for us is should produce something like this for right now. So effectively what we're doing is we're ignoring the idea of person for a second. So write the code that omits person because we're not actually associating with the variable yet, but takes something that looks like that and creates for us something that looks like this. All right, so take a couple minutes and take a stab at that. The code is updated on GitHub. All right, so let's take a look. So what are we building here? We're actually calling our class constructor here. Okay, and our class constructor is going to be built on top of, I'm just going to steal this for right now. We're effectively doing this. Now, what we have right now is we have the idea that we have a class named, it's going to be named person, we're ignoring that, and it's expecting these three parameters. But we don't have the values for that yet. So we don't have this list of values that we need to produce. So in order to get that list of values, we're going to need to actually boil down to a lambda that's going to take in that list of values. So let me just balance back here. So we're going to boil down to a lambda that's going to take in these three pieces of information. Okay, and these three, this is going to be the, so actually, we're going to do this inside of a let so we can be a little cleaner. Okay, so if this is the case, I'm going to create a let where we're going to have a class name is going to be equal to the car of the cooter of code. Then we're going to have a list of params, and this will be the car of the cooter of code. That's going to give us our list of parameters. All right, so that's what our let is going to have in it. And we want to ultimately create something that will generate this for us if we were to provide this list of values. So we're going to boil down to a lambda that's going to take into a parameter a list of values. And actually, I want to call this, I'm going to call this guy list of field names just to make them match. So we're going to have a lambda that's going to take in a list of values. And what is he going to do with it? He's going to generate this class using the list of field names and the list of values that were passed in. Okay, but he's going to give us a lambda as a response. So now when I call parser on our code, is type a reserved word. Let's call this guy kind of statement. Oh, I'm actually missing something there. I think type might have been okay. Because that's my name value pair, and this is my environment for my let. All questions were false. This should be testing it against the string class. All right, so this guy boils down to a lambda. Okay, that's what he gives me. Now, if I were to call that guy, so if I said the parser of code, remember, ultimately this guy's going to be some objects. If I were to say that guy and pass it something like this, Now we get an actual class. So here's our class with all that stuff in it. Okay, so this is the actual thing that happens there. If I were to take that class and apply it to something. Now, realistically, what should happen when I have code that looks like this? Class person is equal to this. This guy here boiled down to a lambda. We want to associate that lambda in our variable environment with our person here. Does that make sense? So now we have a variable environment that, if we drew a picture, we're kind of back to our old standard, I guess close. We have our global environment. So this is our global environment. And inside of our global environment, we want to have a person is equal to this class thingy. That's in our global environment. We want that to exist. Okay. Now, when we create instances of persons, I create an instance of a person, I want to have a first name, last name, and age, and these guys are going to be equal to some stuff. So really, its first name is equal to Mike. Age is 21, something like that. And then we have another, this guy's first name was Dave Smith, and whatever age he was, I say 18. All right. So we have this global environment that is remembering our construct. This is our blueprint for how to build a person that we can then use to create instances of these people. Now, if we go back to what I had earlier, I really had P1 is a person and P2 is a person. So really, once I create instances of these guys, these also go into that global environment. So I have the ability to create a person, and then I should be able to, every time I create an instance of a person in my code, a person is added to my global environment, which then indicates that I now have a new variable scope. That is the variable scope that is associated with an instance of person. So this is P1. This is P2. So those guys effectively create variable environments in and of themselves, which we've already done. We've already written this piece. These guys already have variable environments. What we need to have is we now need to have a global environment that works, that exists for all of these guys, that can then have other code. Now remember, it's the parser that's going to give us our constructs. It's not until we get to the interpreter where we actually have an environment at work. So what we have as a result of calling parser on this code this guy gives us a value, and that value should be associated with what? It should be associated with its variable name value pair. We're ultimately going to want to get that into a environment somewhere. But really what happens in here is when we return our list of values, what we really want to do is we want to create a list containing our class name as well as the value associated with it. Oh, I'm sorry. I put it in the wrong place. It's a list containing our class name along with the value associated with that. So here's a list. Person is the name of the class, and this is the constructor for person. This is what we need to build a person. I pass this guy a list of field names. Actually, I pass this guy a list of parameters to his constructor. So if I say define person, it's already up there. We'll just call this guy person2 to be the result of our parser, like that. This guy is pretty much this, with the exception that I'm no longer providing the field names. It already dictates the field names it should have. When I build a person2, I can now say person2, and he's going to take in a list of parameters. So I'll pass it Mike Littman 21. Oh, sorry. I really need to give it the, because I'm returning the to list, we're not going to directly use it this way. I really need to say catter of this guy on this. And that will build me an instance of person given these parameters to its constructor. You see how this is starting to look more like what Java would look like? We're not interpreting it yet. This is kind of a precursor to our interpreter. But now our parser is giving us the necessary material to then go and build those things. Keeping in mind that, you know, this code here isn't really executable code. This is code that could compile, but we can't run it. You know, this doesn't have a main and it doesn't tell us what to actually do. All right, it's just turning this representation into what is needed to actually create instances of those guys, which is something that is, you know, let's say beyond where we are right this second. So then we have to think about what's the structure of a program. Now, whenever you learn a new language, what do we usually do? We sit there, we write the basic hello world program, right? So we kind of get that template. What is you know, the general template for code in this language look like? Now, even when you first started doing Java, for example, we wrote Java pretty procedurally, where we didn't actually have multiple classes that we then created instances of. Initially, we just had our one class that was just kind of it housed the logic. And what did you have inside there? We had this idea of main, right? We have public static void main, and that's the guy that kind of took over our you know, our code, our program. So really what we might have is, if we think about the structure of our programming language here, we might have a list of let's call it name. Well, let's just call it list of classes. We'll keep it. So we're going to have a list of classes. So we might have a program, and this program is going to have a list of classes. It's then going to have maybe a list of statements, some of which might use those classes. And those statements would effectively be interpreted in order. So for example, we might have something that looks like program. What did I write back here? Something like that. And I'm actually going to kick it down onto some lines just so we can kind of see them separated. So program, and here's my, now this guy's going to be a list of classes. So I actually put it inside of a list. So I have here a single class named person that takes these parameters. Okay, so I'll process my list of classes there. And then I'm going to have my list of statements that's going to have me do something with those classes. So maybe I have something like, here's my list, and I'll actually kind of do this with it. So inside of this guy, maybe I say something like, remember P1 is a person, Mike Littman 21. And similarly, I say remember P2 is Dave Smith 18. And then I might ask P1 get value F name, something like that. And that might be the body of my code. So a program in my new language is going to have a list of classes defined, and we could also have other fields and stuff, but let's just keep it, you know, like other variables defined up here if we wanted to have kind of a global repository of values, but we'll keep it simple right now. So we're going to say this guy has a class of a list of classes that should get defined. Then we're going to have a list of statements that would ultimately need to be processed. Each of these guys needs to be turned into their corresponding, parsed values to then run through the interpreter. So what happens with the results of this? These guys will get wrapped into the environment in which these guys are interpreted. So this is actually what's being interpreted. These guys start off as the starting point for our environment. So it allows us, if you think back to our previous language had like a default environment we created that had like an A, B, and C equal to stuff. And then we had the ability to add variables to our environment. But you know, really what we're doing here is we're describing a global stuff that we want to remember, and that becomes part of the package that we send into our interpreter. So when we parse this, we want to turn it into something that is a collection of things to add to the environment, as well as things that are parsed that also need to be executed by our interpreter. Does that make some sense? So ultimately, what does the parsed version of this thing look like? Steal, well, I'll just steal all of it. And then I'll modify. All right. So ultimately, the package that's going to come out of this probably doesn't need to have the word program in it anymore, because we're going to assume that the thing we're going to send into the interpreter is going to already have a it's going to know about the structure of what's being passed in. So what should class person turn into? Well, the first part of what's going to come out of our parser is going to be a list of two lists. So our parser entirely gives us a list. So the first thing in here will be a list of two lists, where in this case we have a person, and this person will be that lambda thingy that boiled down to. All right, so this is my to list right here. And this is my list of two lists. All right, so we have one parameter that's coming out of that because we are creating a class name person that can be built using this if I pass it the list of parameters. Now, the next thing that's going to come out of this, let me get rid of this, I'll kick it in. Okay, next thing is I now need to have my individual parsed lines. So I'm going to have a list of my parsed statements. Okay, and we're just going to make something up right now because we're basing it off of what we imagine it would be. So maybe this guy would be a, usually we had our stuff named differently inside of our parser, but we'll leave it. Oh, let's just make it lowercase here for our change. So it'll turn into a remember statement. Actually, let's call it that. Remember statement. Passing it P1. And then calling what we call a resolve statement, looking for person, and applying it to something else. So this resolve statement, I'm saying resolve person to be a lambda and apply the result of that to these parameters. Close, open, close. That's probably close. I might be missing a parenthesis. So that's what this line will parse to. It'll parse into a remember statement. And what am I remembering? I'm remembering P1. I'm adding something to my environment. And I'm remembering P1 is apply what? I'm going to apply the result of looking up resolve statement for this, which is going to be a lambda. And I'm applying that lambda to these parameters. This guy is going to be basically the same thing. So I'll just steal. Dave Smith 18. So that's a remember statement. So we're going to remember two things. Now, remember, this is what we're going to feed into the interpreter. Then down here, this guy is going to be a ask statement, where the ask statement is going to, it's going to ultimately, actually, you know what? Let's send message statement, just so it's really connecting the dots with what we did last time. So this would be a send message statement. And who are we sending the message to? We're sending it to P1. So we're gonna actually have to resolve P1. That's the who. What message are we sending? This guy, which is a literal. So we can lit statement, something like that. And then this is the value, lit statement. F name. So something along those lines. So the output of our parser would give us effectively this package. Okay, a package that is a list containing a list of classes followed by a list of statements to execute with those classes in mind. So then when we build our interpreter would go through, it would add all this stuff to the environment first, and then execute sequentially these statements within the environment that was extended with that information. All right, does that make some sense? So, oh, go ahead. Oh, so was that a C, senor?
C.
C. All right, so for Thursday, I'm not going to have you write anything from this because we've pretty much already written remember statements. We've written send message. We're just thinking about pulling this apart as a package, and we'll look at this some more on Thursday. But for Thursday, review our slides and come with any questions you have for the final exam. The final exam will be up by Sunday at, let's say Sunday by midnight. It'll be designed to take about an hour. I'll give you like 2.5 hours time limit, so it shouldn't be a time constraint type situation. You just need to do it sometime during the week before midnight Friday, so I have time over the weekend to grade it. But look through the notes, decide if you have anything you want me to review, and I'll spend the first part of class on Thursday reviewing anything you want me to go over, and then we'll kind of finish up this conversation of how our interpreter might deal with this. All right, questions, comments, concerns, bribes? All right, I'll see everybody on Thursday.